Hello everyone, myself Orisina Mohapatra and I'm a third year student of EC department of Coachbehar Government Engineering College. And today I'm going to discuss about the topic of operation of MOSFET, which is under the subject of CMOS VLSI Design. So let's start our topic. So firstly, the introduction to MOSFET. The metal oxide semiconductor field effect transistor, or simply called as MOSFET, represents the cornerstone of modern integrated circuit technology. As the most critical active device in CMOS VLSI circuits. MOSFETs have revolutionized the electronics industry by enabling the creation of increasingly complex and powerful systems. So here are 4 points that why we should use MOSFET or why the MOSFET is used universally. The first point is voltage control device. Unlike bipolar transistor, MOSFETs operate using voltage rather than current, providing superior control characteristics. The second point is switch and amplifier. It serves dual roles in digital switching applications and analog signal amplification circuits. The third point is digital IC foundation. It forms the building blocks of processors, memory units, and all modern digital integrated circuits. And the last point is power efficiency. High input impedance and minimal static power consumption make it ideal for battery powered device. So here are the MOSFET structures and components. A MOSFET comprises 4 distinct terminals that enable its operation. The device structure features a sophisticated arrangement of semiconductor materials and insulating layers that facilitate controlled current flow. So the 4 fundamental terminals of MOSFET. Firstly, the gate, the source, the drain, and the substrate or the body. The function of the gate is control the channel conductivity through applied voltage. The source emits charge carriers into the channel. The drain collects charge carriers from the channel, and the body provides the semiconductor functions. And here are some key structural elements that the gate is separated from the substrate by ultra thin oxide layer of silicon oxide. The source and the drain are heavily doped regions creating ohmic contacts. The conductive channel forms between the source and the drain when gate voltage exceeds thresholds. So here we can see a clear picture of the MOSFET structure. Firstly, there is the source and here is the drain, which is situated inside the substrate or the body. The source is which emits charge carriers into channel, and the drain is which collects charge carrier from the channel. And between the source and the drain, here is the channel region. And upside of the substrate, here is the gate, which controls the channel conductivity through applied voltage, and the gate is separated from the substrate by a small strip of silicon oxide. Moving to the next slide, the working principle of MOSFET. The fundamental operation of a MOSFET relies on electric field control rather than current injection. The field effect mechanism distinguishes MOSFETs from bipolar junction transistor and provides several key advantages in circuit design. So here are some advantages of the MOSFETs which distinguish itself from the bipolar junction transistor. First point is the gate voltage applied. The voltage at gate terminal creates electric field across oxide layer. Secondly, the field penetrates. Electric field penetrates through thin oxide into semiconductor substrate. Thirdly, the channel formation. Field controls charge carrier concentration, creating conductive channel. And fourthly, the current modulation. Channel conductivity varies precisely with gate voltage magnitude. Crucially, no direct current flows into the gate terminal due to the insulating oxide layer. The result in extremely high input impedance, making MOSFETs ideal for voltage amplification and switching applications. The device operation fundamentally depends on the gate to source voltage VGS, which determines whether a conductive channel forms between source and drain. Now the modes of operation of the MOSFET. The MOSFET operates in 3 distinct regions, each characterized by different voltage relationships. Understanding these operating regions is essential for designing both analog and digital circuits. So here are the three modes of operation. The first mode of operation is the cutoff region. The condition of this operation is VGS should be less than VT. No channel forms between source and drain. Device behaves as an open switch with negligible current flow. The second mode of operation is the triode or linear region. The condition is the VGS should be greater than VT and the VDS should be less than VGS minus VT. The channel forms and MOSFET behaves as a voltage control resistor. Current increases linearly with drain source voltage. And the third mode of operation is saturation region. And the condition of this operation is VGS should be greater than VT and the VDS should be greater or equal to VGS minus VT. The channel pinches off near drain terminal. Device acts as a constant current source, ideal for amplification. These regions are determined by the relationship between gate source voltage VGS and the drain source voltage VDS, with VT representing the threshold voltage required to form the channel. In this slide, we would discuss about the cutoff region operation. So the operation conditions, as we have read earlier, that the MOSFET enters cutoff when the gate to source voltage is less than the threshold voltage, or simply the VGS is less than VT. Physical behavior of this operation: no conductive channel forms between source and drain terminals. Charge carrier concentration remains insufficient for conduction. MOSFET remains in off state in minimal leakage current. Drain current approaches zero. Practical applications of the operation: the region enables MOSFET to function as open switches in digital logic circuits, representing the logic zero state. The high impedance in cutoff ensures minimal power consumption when the device is switched off. So here in the picture, we can see the cutoff region operation, the source and the drain, and in this operation, it is clearly showing the operating condition that VGS should be less than VT. In the next slide, we would discuss about the triode region operation or the linear region operation. The operating conditions are VGS should be greater than VT and VDS should be less than VGS minus VT. The physical behavior of this operation: conductive channel fully forms between source and drain. MOSFET behaves as a voltage controlled variable resistor. Drain current increases approximately linear with VDS and the channel remains uniform throughout its length. Now the current relationship. The drain current follows a relationship with the other parameters by this equation. We can see here that the drain current ID is equal to mu n into COX into W by L into VGS minus VT multiplied by VDS minus VDSS whole square by 2. The applications of this region is: it is widely used in analog circuits, transmission gates and linear amplification stages where variable resistance behavior is required. Now in this picture of region linear region operation, we can see that the conditions that VGS should be greater than VT and the VDS should be less than VGS minus VT. And here we can see that a channel is formed between the source and the drain. In the previous picture, we have seen that there is no channel formed. So it is the cutoff operation, and in this picture we can see that a channel is formed and the channel is nearly uniform throughout the length. So it is that is why it is called the linear region operation. In this slide, we will discuss about the saturation region operation. The operating conditions are: VGS should be greater than VT and VDS should be greater or equal to VGS minus VT. The physical behavior of the operation is channel pinches off near the drain terminal. The drain current becomes almost constant regardless of further various increases. MOSFET acts as a current source and it pinches off occurs because the VGT is less than VT at drain end. That is why the pinches off occurs. The current relationship, the drain current uh, relates with the other parameters as the drain current is ID is nearly equal to half of mu n into COX into W by L into VGS minus VT's whole square. Current depends only on gate voltage, not drain voltage. It is the most important point. Now the applications of this operation essential for amplifiers, CMOS, logic gates and analog circuits requiring constant current source. So where we need the constant current source, we can use this operation. Here in the picture you can see that it is the saturation operation. The conditions are clearly shown that VGS should be greater than VT and VDS is greater or equal to VGS minus VT. And here you can see in this channel region that the channel is pinches off near the drain point. So that is and the current becomes saturated. So in the next slide we will see the importance of MOSFET in CMOS VLSI. The MOSFET technology underpins the entire modern electronics industry, enabling the exponential growth predicted by Moore's law. The unique characteristics of MOSFET make them indispensable for contemporary integrated circuit design. Low power consumption. CMOS circuits consume minimal static power, with current flowing only during switching. These enables battery powered device and reduce cooling requirements in high performance systems. High switching speed, fast transition times between logic states enable clock frequencies exceeding several gigahertz, supporting modern processor architectures and high speed digital communication. Excellent scalability. MOSFET scale effectively to nanometer dimensions, allowing billions of transistors on single chips. Continued miniaturization drives performance improvements while reducing cost per function. CMOS logic implementation, complementary MOS or CMOS technology uses both NMOS and PMOS transistor, providing robust logic gates with excellent noise immunity and power efficiency. Memory and processor design, foundation of SRAM, DRAM, flash memory, and microprocessor architectures enables complex computing system from mobile devices to supercomputers. Modern VLSI backbone, very large scale integration relies entirely on MOSFET technology, enabling system on chips design that integrate complete computing systems into single semiconductor die. So thank you guys for your attention and engagement with the presentation on MOSFET operation in CMOS VLSI circuits. So here our presentation ends, and the last but the not least, the acknowledgement part. This presentation draws upon standard CMOS VLSI design textbooks and academic resources, and special thanks to our course instructor and teaching assistant for their guidance. Thank you.